In the last section, we introduced the dual formulation of a given primal problem. Let's assume we solve the dual problem. Here we may have a question. Is the optimum of the dual problem the same as the primal optimum? If not always, when are they the same? These questions are the core of weak duality and strong duality. We'll study them in this section, and we'll consider some details of complementary slackness. Here is the problem we are trying to solve. This is the given problem, the primal problem. Its Lagrangian is defined as in this equation, and here alpha and beta are Lagrange multipliers. The given problem can be equivalently formulated as the minimax problem or min-max problem, minimization over x and maximization over the Lagrange multipliers. That is equivalent to the original problem. So we call it the primal problem, and its dual problem is maximum problem by changing minimization and maximization, the order, different order. So we call it the dual problem. The dual function, or the Lagrange dual function, is defined as here g of alpha beta, which is minimization over x of the Lagrangian. For the Lagrangian is always lower bound of the primal optimum. That's what we have done so far. Now we'll go to duality. The dual problem is a lower bound for the primal problem. That means that the primal optimum is always larger than or equal to the dual optimum. This inequality can be proved quite easily. Here in fact, earlier we saw that, but here we try to prove once more. Now, along with the Lagrangian, now if we take minimum over x, then this inequality is true. Now, if x is the minimizer, well, then we can write in this way. Now, for the Lagrangian, if we take maximum over the Lagrange multipliers, then this inequality is also true. If alpha star, beta star is the maximizer, then we can write in this way. Now, for the same Lagrangian, we are taking minimum over x and maximum over the Lagrange multipliers, then again this inequality is true. Now for this one, we already know that this one, and for this right side, that is the same as now over there. Now we focus on this term and that term. Then this inequality is true for all possible x and alpha and beta. Of course, alpha must be non-negative. Then, now this is always true. So that even though you are taking maximum over the Lagrange multipliers and taking minimum over Lagrange multipliers, this inequality must be true. That is exact exactly this one. Okay, so we can recheck this inequality. Always true. So this inequality is always true, and that is called the weak duality. And for some cases, these are the same. Then in the case, we say the strong duality holds. That is the definition. Now we'll go to the strong duality. Here we have the Slater's theorem. We assume that the primal problem is a convex problem, and also there exists at least one feasible, strictly feasible x tilde satisfying these Slater's conditions. Here the inequality constraint is strict at the position for every component, and now the equality constraint is satisfied. At least one point is there, then now the problem holds the strong duality, which means that its dual problem, dual optimum, must be same as the primal optimum. Okay, in this area is quite related with the concept of duality gap. We define the duality gap in this way. By definition, f of x minus g alpha beta, that is dual function, and it's called the duality gap. And by taking minimum and by taking maximum, we reach at here now f star minus g star. So this inequality is true. And we know that this is always larger than equal to 0. So that we have that. Now, the strong duality is observed here with by taking optimum, it must be 0. Okay, here we have now with x and alpha beta, the duality gap equals to 0 if and only if x is the primal optimal solution and alpha beta is the dual optimum. And now the strong duality holds, so that this gap will be 0 when these are the optimal the values, and then strong duality holds. Okay, so strong duality holds, then along with the dual problem, we can reach at the primal optimum. Okay, here we have a proof, but its proof is quite simple one. Okay, now we have complementary slackness. Now here we'll assume that the strong duality holds, and x star is the primal optimum and alpha beta is the dual optimum. Then now f star, f at x star, and g of alpha star, beta star, it will be the same. This gap, duality gap must be 0, so that they must be the same. And by definition, this one, and we consider the detail of the Lagrangian, then we reach at this one. Now, here, once we try to choose alpha, beta, and alpha is non-negative, and then here this is non-negative, so that okay, this is non-negative, this is non-positive, so here this is non-positive, and then now there will be 0. because these terms are 0. So we can reach this inequality. It's the same when this term is 0, which means that alpha I star hix star is 0 for all I. That is called the complementary slackness. One is one part is larger than 0, so it's slack, it's loose. Then the other part must be tight. And now that is loose, the slack, then the other part must be 0. So one of them is non-zero, then the other must be 0. So it is non-zero, or means it's loose and slack, so that the name comes from that observation, complementary slackness. Here we have a note. The complementary slackness says that if a dual variable is greater than 0, which is slack, then the corresponding primal constraint must be on equality, tight. So the other way, and if the primal constraint is slack, loose, then the corresponding dual variable must be tight, which means must be 0. Okay. In computation, the complementary slackness is the key to designing primal dual algorithms. The basic idea is here, start with a feasible dual solution and try to find primal feasible x such that now x and alpha. So we try to say here now only alpha, and beta can be arbitrarily the quantity, so that we consider only in alpha feasible region, which means non-negative. So the x alpha satisfies the complementary slackness. Once you can find this x alpha satisfying the complementary slackness, then you're done. Otherwise, by using the misfit, you can now modify alpha, and you can repeat step 2. So start with alpha and try to find the x, feasible x satisfying the complementary slackness. If not, then the misfit on x can modify alpha, and now you can find again the x. So keep going in this way so that you can find eventually the optimal solution. And that's how the algorithm is designed. Most of the algorithm is based on this basic idea. Okay. Okay, that's the end of the section. Thank you.